In this video, we are going to talk about eigenvalues and eigenvectors. But before that, let us understand what is a characteristic equation. Consider a matrix A 1, 2, 4, 3. Let us find out lambda I, where lambda is a non-zero scalar and I is the identity matrix of the order of matrix A. So we write lambda into 1, 0, 0, 1. That gives us lambda 0, 0 lambda. Now let us subtract this lambda I from A and write A minus lambda I. That will be 1, 2, 4, 3 minus lambda 0, 0 lambda. That will be 1 minus lambda, 2, 4, 3 minus lambda. This is A minus lambda I. So this matrix is known as characteristic matrix. If we write determinant of this characteristic matrix, it will be determinant A minus lambda I equals determinant 1 minus lambda, 2, 4, 3 minus lambda. This will give us a polynomial known as characteristic polynomial, and after evaluation this characteristic polynomial will be 1 minus lambda into 3 minus lambda minus 4 2s are 8, or lambda minus 1 into lambda minus 3 minus 8. That will be lambda square minus 4 lambda plus 3 minus 8, which finally will be lambda square minus 4 lambda minus 5. Now if we equate this characteristic polynomial to 0, then the equation that we get, lambda square minus 4 lambda minus 5 equals 0, is known as characteristic equation. This characteristic equation is a quadratic equation in lambda, which can be solved by factorizing this quadratic polynomial, which will be lambda minus 5 into lambda plus 1 equals 0, and this gives two values of lambda, the first being lambda equals 5 and the second being lambda equals minus 1. Now these values of lambda are known as eigenvalues or proper values, because the word eigen in Germany means proper. So these are eigenvalues or proper values of the matrix A 1, 2, 4, 3. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. Now for matrix A 1, 2, 4, 3, we have two eigenvalues, lambda 1 equals 5 and lambda 2 equals minus 1. Now corresponding to eigenvalue lambda 1 equals 5, suppose we have a column matrix X such that matrix A minus lambda 1 I into X equals 0 matrix O, which will be matrix 1, 2, 4, 3 minus 5 into unit matrix 1, 0, 0, 1. This multiplied by X equals the 0 column matrix 0, 0. This will be 1 minus 5, 2, 4, 3 minus 5. In place of X we write x1, x2 equals 0, 0. This will be minus 4, 2, 4 minus 2 into x1, x2 equals 0, 0. We will reduce this matrix into row echelon form in order to find the values of x1 and x2. For that, we will perform row transformation R2 plus R1. That gives minus 4, 2, 0, 0. Matrix multiplication gives us a linear equation in x1 and x2, that will be minus 4x1 plus 2x2 equals 0. Since there are two variables in the equation x1 and x2, we have to assume x1 equals parameter t, so that 2x2 will be equal to 4t or x2 equals 2t. Now putting t equals 1, we get x1 equals 1 and x2 equals 2. So the vector x equals 1, 2 will be called eigenvector, or any non-zero multiple of x will be called eigenvector corresponding to the eigenvalue lambda 1 equals 5. Now corresponding to second eigenvalue lambda 2 equals minus 1, we write matrix A minus lambda 2 I into matrix X equals 0 matrix O. Substituting the values, we write for A 1 2 4 3 minus of minus 1, that will be plus I, all this multiplied by matrix x1 x2 equals 0 0, that will be 1 plus 1 2, 2 plus 0 2, 4 plus 0 4, 3 plus 1 4, multiplied by matrix x1 x2 equals 0 0. By row transformation R2 minus 2 R1, we will reduce this matrix into row echelon form, and that will be 2 2, 4 minus 4 0, 4 minus 4 0, x1 x2. Matrix multiplication will be 2x1 plus 2x2 equals 0, that will be x1 plus x2 equals 0. Since there are two unknowns x1 and x2, let us assign parameter t for x1 so that x2 becomes minus t. If we put t equals 1, x1 becomes 1 and x2 becomes minus 1. So the vector x will be 1 minus 1, which will be the eigenvector corresponding to the second eigenvalue minus 1. Let us understand what is sum and product of eigenvalues. For that, let us consider matrix A of order 3, A1, A2, A3, B1, B2, B3, C1, C2, C3. Its characteristic equation will be determinant A minus lambda I, where lambda is a non-zero number, equals 0. This will be A1 minus lambda, A2, A3, B1, B2 minus lambda, B3, C1, C2, C3 minus lambda. We will equate this determinant to 0. Expanding this determinant, we will get lambda cube minus A1 plus B2 plus C3 lambda square plus A1 B2 plus B2 C3 plus C3 A1 minus A2 B1 minus A3 C1 minus B3 C2 multiplied by lambda minus determinant of A equals 0. For a polynomial A0 x power n plus A1 x power n minus 1 plus A2 x power n minus 2 plus so and so forth, A1 equated to 0. For this polynomial equation, we have sum of roots equals minus A1 upon A0 and product of roots equals minus 1 power n into an upon a0. Roots of this equation 1 will be the values of lambda, which are nothing but the eigenvalues of this matrix A. Now if we compare this equation 1 and this equation 2, these sum of roots, that is sum of the eigenvalues, equals minus a1, that is minus this a1, which is nothing but a1 plus b2 plus c3. So here a1 plus b2 plus c3, which is nothing but sum of the diagonal elements a1, b2 and c3, and product of eigenvalues will be product of roots minus 1 power n an upon a0. Here this an is minus determinant of a, so minus 1 power n into minus determinant of a will be equal to determinant of a. So we get sum of eigenvalues equals this minus and this minus, that is sum of diagonal values of the matrix a1 plus b2 plus c3, and product of eigenvalues equals this determinant of a. So this is the final result that we get. Now we will solve a problem based on this. If lambda 1, lambda 2 and lambda 3 are the eigenvalues of matrix A minus 2, minus 9, 5, minus 5, minus 10, 7, minus 9, minus 21, 14, then we have to find sum of eigenvalues lambda 1 plus lambda 2 plus lambda 3 and product of eigenvalues lambda 1, lambda 2 and lambda 3. Like what we have just seen, sum of eigenvalues equals sum of diagonal elements, that is sum of -2, -10 and 14. So -2 -10 plus 14 will be 2. So lambda 1 plus lambda 2 plus lambda 3 is 2. Next we find product of eigenvalues equals determinant of matrix A, that is lambda 1 into lambda 2 into lambda 3 will be determinant of matrix A -2 -9 5 -5 -10 7 -9 -21 14. This will be -2 into -10 into 14 -140 -7 into -21, that will be -147. So minus and minus will become plus 147. Next, minus of this -9, that will be plus 9 into -5 into 14 -70 minus of 7 into -9 -63. So minus of -63 will be plus 63 plus this 5 multiplied by -5 into -21 105 minus 10 into -9 plus 90, that will be -2 into 7 plus 9 into -7 plus 5 into 15, that will be -14 -63 plus 75, that will be -2. So finally we get sum of eigenvalues equals 2 and product of eigenvalues equals -2. Let us learn second property, property 2 of eigenvalues. If lambda 1, lambda 2, lambda 3, so on and so forth, lambda n are the eigenvalues of a matrix A, then determinant of A equals lambda 1 into lambda 2 into lambda 3 into so and so forth lambda n. This can be proved as follows. Since lambda 1, lambda 2, lambda 3, so and so forth lambda n are the eigenvalues of matrix A, we know that the characteristic equation determinant A minus lambda I equals 0. Now this characteristic equation will be a polynomial equation whose roots will be the eigenvalues lambda 1, lambda 2, lambda 3, so and so forth lambda n. Therefore we can write determinant A minus lambda I equals -1 power n into lambda minus lambda 1 into lambda minus lambda 2 into lambda minus lambda 3, so on and so forth into lambda minus lambda n. Here we will put lambda equals 0. So this equation will reduce to determinant A minus 0 into I, that will be determinant of A equals, by the rule of product of eigenvalues, -1 power n into this -1 power n into minus lambda 1 into minus lambda 2 into minus lambda 3, so on and so forth into minus lambda n. Therefore we can write -1 power n into -1 power n and minus sign of each lambda. We get determinant of A equals lambda 1 into lambda 2 into lambda 3 into so and so forth into lambda n. So this is the property that we have to prove, this one. Third property of the eigenvalues, property 3, is if matrix A is singular, which means determinant of A equals 0, then at least one of the eigenvalues is 0 and vice versa. Now this can be easily proved. We have just proved that if lambda 1, lambda 2, lambda 3, so on and so forth, lambda n are the eigenvalues of this matrix A, then determinant of A equals product of the eigenvalues lambda 1 into lambda 2 into lambda 3 into so and so forth lambda n. But this matrix A is singular, therefore determinant of A equals 0, which means at least one of these eigenvalues is 0. Or conversely we can say that if at least one of these eigenvalues is 0, then determinant of A is 0, provided matrix A is a singular matrix. Third property of the eigenvalues, property 3 is if matrix A is singular, which means determinant of A equals 0, then at least one of the eigenvalues is 0 and vice versa. Now this can be easily proved. We have just proved that if lambda 1, lambda 2, lambda 3, so on and so forth, lambda n are the eigenvalues of this matrix A, then determinant of A equals product of the eigenvalues lambda 1 into lambda 2 into lambda 3 into so on and so forth lambda n. But this determinant A is singular, but this matrix A is singular, therefore determinant of A equals 0, which means at least one of these eigenvalues is 0. And conversely, we can say that if at least one of the eigenvalues is 0, or conversely we can say that if at least one of these eigenvalues is 0, then determinant of A is 0, provided matrix A is a singular matrix. Let us find sum and product of the eigenvalues of matrix A. 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3. We have just proved that sum of eigenvalues equals sum of the diagonal elements, which are these 8 7 and 3. Their sum will be 8 plus 7 plus 3 18, and product of the eigenvalues will be determinant of matrix A, which will be this 8 multiplied by 7 3s are 21 minus 4 4s are 16 minus this minus 6, that will be plus 6 into minus 18 minus minus 8, that will be plus 8 plus this 2 into 24 minus 14, that will be 8 multiplied by 5 plus 6 multiplied by minus 10 plus 2 multiplied by 10, that will be 40 minus 60 plus 20 0. So sum of the eigenvalues is 18 and product of the eigenvalues is 0. In a matrix A, B, C, B, C, A, C, A, B, A, B, C are positive integers, then we have to prove that number 1, A plus B plus C is an eigenvalue of matrix A. Number 2, if A is a non-singular matrix, that is, if determinant of A is not equal to 0, then one of the eigenvalues is negative. Let us first write the characteristic equation of matrix A, which will be A minus lambda B C minus lambda A C A B minus lambda. Determinant of this equals 0. By elementary transformation, C1 plus C2 plus C3, we get A minus lambda plus B plus C, that is A plus B plus C minus lambda B C. Then B plus C minus lambda plus A will be A plus B plus C minus lambda A. Then C plus A plus B minus lambda will be A plus B plus C minus lambda A and B minus lambda. Determinant of this is 0. Now the elements in the first column being all equal, we will take them as a common factor and write A plus B plus C minus lambda into 1 B C 1 C minus lambda A 1 A B minus lambda. Determinant equals 0. Now since the product of these two numbers is 0, either of them is also 0. So we write A plus B plus C minus lambda equals 0, which implies A plus B plus C equals lambda, which is an eigenvalue of determinant A. Now this is the answer to our first question. Now if lambda 1, lambda 2, lambda 3 are the eigenvalues of matrix A, then we have seen that lambda 1 plus lambda 2 plus lambda 3 equals sum of the diagonal elements A, B and c. But here a plus b plus c is lambda, so one of the eigenvalues lambda 1 equals a plus b plus c. So if we put this lambda 1 equals a plus b plus c, then a plus b plus c plus lambda 2 plus lambda 3 will be a plus b plus c. This a plus b plus c gets cancelled and we get lambda 2 plus lambda 3 equals 0. We name this equation 1. Now if matrix A is non-singular, then determinant of A is not equal to 0, but determinant of A equals product of these eigenvalues lambda 1, lambda 2, lambda 3, which is not equal to 0. We name this equation 2. Now from equation 2 we find that none of these eigenvalues is 0, and from equation 2 we get lambda 2 plus lambda 3 equals 0. That implies one of the values of lambda 2 and lambda 3 is negative, and that proves our second statement. Friends, if you like this video, please click the like button, share this video with your classmates. Don't forget to subscribe this channel to get more videos of this type. Give your comments to make these videos better. You can suggest topics on which you want me to make videos. See you in the next video. Until then, keep watching Number Collage. Thank you.